All right, so what's going on in this scenario? Go ahead. Okay. So there's a dog and they're going away from this post, right? And it's a function of time. So when we say f of 60 equals 4, we're saying at time 60, the dog is 4 feet away from the post, right? Does that make sense? Okay, so when we say f of 140, and that was 3.5, what are we saying in context? Like, how would we write that out? So
140, the dog 25 feet away from the post.
Does that make sense? Okay, that's on your mastery check for Thursday. So it might say something like, find this, and then interpret it in context. So the interpreting piece would be this little scenario. Does that make sense? Okay, on your graph, it also tells you this on the X and Y axis. So make sure that you're paying attention to that, okay? So today, we're going to identify characteristics of functions as we examine graphs using interval and set notation. So let's think about what characteristics mean. So what do you think characteristics of a good best friend is? Like your bestie has these characteristics. Yep. Loyal. Yeah. You gotta tell all your secrets to them. Yep. Funny. They gotta be funny. If they ain't funny, they out. Right? Anything else? Yep. Supportive. Okay. What about a good teacher? What are good characteristics of good teaching? Understanding. Good. Attitude. What do you mean? Like not have a bad attitude? Oh, okay. Cool. All right. Anything else? Skills. So like actually know the content, right? Like, have you ever had like a math teacher that didn't know what they were doing? Yeah. Okay. It's not me. It's fine. All right. What about characteristics of a math classroom? Math classroom. What does that look like? Math. Okay. Say it again. Like math language. Okay. What else? Numbers. Okay. Like a good math classroom is going to be like the teacher shows you examples and then like you kind of work the problems, right? Okay. So really quick, we've got a toy rocket and a drone. Were launched at the same time. Here are the graphs representing the heights of the two objects as a function of time since they were launched. Height is measured in meters above the ground and time is measured in seconds since launch. So analyze the graph and describe as precisely as you can what's happening with each object. Which parts or features of the graph show more important information with each object's movements? List the features or mark them on the graph. Okay, so really quick, let's think about this. This guy's the rocket, right? R is for rocket. Okay, so we're launching a rocket. What does this represent? Like, what's some more important key features here? Go ahead. So the initial value? Okay, so where they started. Okay, what else is important on here with the rocket? The time it took. Time it took for what? To descend. Okay, so how long it was in the air? Where it landed? What about this point? What is this called? That red dot. What is that called? What is this called? A dot, okay. So we're going up, and then we're going to start going down. So that's the maximum. Another word that we use is vertex, right? Okay. So really quick, let's think about a drone. When it takes flight, right, it starts from the ground, right? So right here, this is where it starts on the ground. And then it goes up and then it reaches like a specific height, and then it kind of does what? It kind of hovers and it kind of goes side to side. It's kind of like a helicopter, right? So right here, there's this little constant area. So this is where it's like hovering, right? I spell hovering. Is that right? Okay, cool. All right, and then it starts to descend, right? So it's decreasing right here, and then this is where it lands, right? So how long was it in the air, the drone? 7 seconds, right? We're going to go over x-intercepts. What are x-intercepts? So when it crosses the x-axis, okay? So what does that mean in like real life terms? Well, when it hits the x-axis, this is talking about the time it takes, how long it takes for it to be in the air, right? So how long it's in the air. All right, so for function r, we're looking at the x-intercepts. So it crosses the x-axis one time, right? And this is going to be at 5, 0. And this is where it lands at the end. Now for function d, we've got 2 x-intercepts. We got this guy and this guy. So we got 0, 0, and 7, 0. 7, 0 is where it lands. What is 0, 0? All right, so where it starts, right? Okay, so for the y-intercept, that's where it crosses the y-axis, right? This is also going to deal with the height of the object or the initial height of the object. Okay, so you just asked a really good question. Why don't we have the initial or where the rocket started? Well, it starts right here, right? And that's at 0, 25. Let's do that right. So that's 0, 25. So that means that the rocket was 25 meters in the air. Okay, so that's like if you stood up on a ledge and you were just like, yeah, throw the rocket, right? Or the drone. Where did it start? Or what was its initial height? 0. So it was 0 meters off the ground. A lot of people struggle. Domain and range in context. Okay, so domain deals with my x values, and range deals with my y values. But when we talk about domain, we're talking about how long it's in the air. Kind of similar to what our x-intercept is, kind of similar. But domain is talking about the interval of time that it's in the air. Okay, for instance, with function r, we go from here to here. So we go from 0 to 5. So our domain is from 0 to 5. And this time we're going to use these little brackets. Can you find the domain for function d? Okay, so what's the domain for function d? 0 to 7, right? Ta-da! Not too shabby. Okay, with the y values, so with the range, this is talking about the height of the object. Okay, so where it starts to where it goes, or how high it goes. So for instance, on function r, we go from I'm sorry. Yeah, we go from down here, because it touches down here, up to here. So this is going to be from 0 to 45. Can you find the range for function D? So my range for function D is going to go from 0 to how high? 20, right? So we're going to go from 0 to 20. Any questions on that? Okay, so when you're doing domain and range, what I like to do is I kind of like to box my information in. So kind of like how I'm drawing these lines, I'm going from this to this, and that's how I write out my range. If I was doing my domain, I would go here to here. Okay, use those lines to kind of help you. Okay, we're going to talk about one more thing, intervals of increase and decrease. All right, so intervals of increase and decrease. So intervals of increase tells me when the function's y values go up. The decrease tells me when the function's y values go down. So we'll start with R first. So R, it goes up, 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 and then it goes down.
It's fine for both of them.
So we're going to look at the X values. So we're going to state the X values, but the Y values tell us whether we're going up or down. Yeah. When I do increase and decrease, I always want to think of myself on like a Six Flags ride. Am I going up or down? Right? So I'd be going up on this one and then going down. So for function R, we're going up between 0 to 2. So we're going to say from 0 to 2. And then when is it going down? Well, it's going down from 2 to 5. Can you find the interval of increase and decrease for function D? All right, so looking at function D, we have it's going up right here. What about the straight line across? What is that doing? It's constant, right? So that's neither increasing nor decreasing, right? Okay, so when we write our interval of increase, we're going to go from 0 to 2. And then when we decrease, we're going to go from 5 to 7. Everybody see that? Okay. Questions on that? All right, we're going to change gears just a little bit. Okay, so I want you to take out the paper that says scootering around Atlanta. The one that says scootering around Atlanta. Okay, so we're going to do a little task really quick. Okay, so how many of y'all have ridden a e-scooter before? Do you know what those are? Just one person? Oh my goodness. Okay, cool. Have ridden an e-scooter before? Some of you haven't. These are the little scooters that they kind of like leave around the city, and you can like pay to ride them around and everything. Sometimes they're beneficial and sometimes they're just expensive for no reason, depending on where you're going, right? So today we're going to use function notations, linear functions, and unit rates to determine if this person, I don't know how to say that, has enough money to have lunch and ride a scooter from Pont City Market to Centennial Olympic Park. How many of you have been to Pont City Market? Yeah. Okay. I feel like we need to do a field trip. That's what needs to happen. It's a little expensive. That's fine. All right. So She's visiting Atlanta and will be renting an e-scooter to get around. The e-scooter company uses an app to accept payments for renting the scooter. In the app, it states that the function C of T gives this cost of renting the e-scooter in dollars for T minutes. Based on the app's previous data storage, she knows that C of 2 equals 1.5 and C of 5 equals 2.25. So really quick on your paper, I want you to tell me, what does each equation tell us about renting an e-scooter? So right here, what information does this tell us? Ooh, right on your paper, right on your paper. Let's share out. You said the cost. Okay, the cost of what? Cost of scooter is going to be what? $1.50 for what? For 2 minutes of riding around, right? Can you get anywhere in like 2 minutes? Like, couldn't even make it down the street, right? That would be horrible. Okay, what about this one? Fantastic. Okay. Go ahead and take a moment and go ahead and fill in the next section. So use function notation. So function notation is what we just had, this guy. Okay, so you're writing out a function notation for it costing $1 to unlock the e-scooter and it costing $3.50 to ride the e-scooter for 10 minutes. Go ahead and complete that. Okay, so first thing, it says it costs $1 to unlock the e-scooter, right? Okay, so if I'm not going anywhere, I'm just unlocking the scooter. I haven't rented it for any amount of time, right? That C of 0 equals how much? So if I just want to get the scooter out, it's going to cost me $1, right? Okay, on the next one, it says it costs $3.50 to ride the e-scooter for 10 minutes. So that's saying, hey, for 10 minutes, it's going to cost me $3.50. This is what I was asking you to write on those two problems. Okay. Now, when you graphed it, you should have something that looks like this. So you see these lines or these dots? If I connected all these dots, what kind of function do I got going on? Linear, how do you know? Boom, straight line. So really quick, we've got 2 is the input or the x coordinate, and 1.5 is the output or the y value. Now, part 2 asks you to write the equation. Okay, we have learned about linear equations, and you know this equation. What is this equation called? What's the name of this guy? Slope intercept. Okay, so this guy's the slope, and this guy's the y-intercept, right? So really quick, let's talk through this. So we're going to try to write an equation. So we're going to put C of t. So on part 2, you're putting C of t equals. Now, m is going to be 0.25. The way I got that is when it told me that C of 2 was 1.5, I know that it costs $1 to get that e-scooter out, right? So if I subtract $1 off of that, that's going to give me 0.5. And we rented it for 2 minutes, right? So I'm going to divide by 2. So that gives me 0.25. So that's why my slope is 0.25. I know that was a lot, so I'll give you a second. So this y-intercept is our initial value. Again, if we didn't go anywhere, it would cost us $1 just to get that scooter out, right? Fun, take a moment. You're working on part. Okay, so she's budgeted $15 for a visit. First of all, she don't have enough money, but it's fine. All right, if she spends $10 on her lunch at Ponce City Market, she'll have enough money to scooter the Centennial Olympic Park. Will she have enough money? The park is 2.5 miles, and it can travel up to 10 miles per hour. So first of all, we got to figure out this whole like 2 miles, 10 miles per hour business. So when I say 10 miles per hour, how many minutes are in an hour? 60, right? Okay. So in 60 minutes, she can travel 10 miles, right? Okay, let's just divide that in two. In 30 minutes, how many miles is she going to have? All right, let's divide that in two again. That's going to give me 2.5 miles, right? So how long is it going to take her to go 2.5 miles? Okay, now we had an equation from the previous page. What was that equation? Fantastic. So we're going to plug in for t what number? Okay, so let's do that. 0.25 times 15 plus 1. I'm going to use my calculator, and I'm going to get 4.75. Exactly. Now, she started with $15. She spent 10 of it on lunch, and she had $5 left, right? Well, how much is it going to cost her to travel? But will she have enough? Yeah, she'll have enough, and she'll have 25 cents where she can go buy a piece of gum or something, right? Yeah, that's about it. That's all she can buy, right? Can you take a moment? Can you try the next one? So let's say we can only go 5 miles. Ready? Okay, so 5 miles per hour, right? So that means that in 60 minutes, how far she can go? 60 minutes, how far can she go? 5 miles per hour. In 60 minutes, how far can she go? 5 miles. Okay. In 30 minutes, how far can she go? 2.5. Okay, so notice how we're different from what happened up here, right? We're saying that she'd be slower. Okay. What about in 15 minutes? How far? 1.25. That's okay. All right. So now we're going to take our equation. And I saw that some of you were taking these numbers and plugging them in. We're not plugging those in. Remember, we're plugging in the minutes. Plugging in the minutes. So let's take 60 and plug it in. If we threw this in our calculator, we would get 16. Well, can she spend $16? No, why? She only has $15 in her pocket, right? Okay, so that's not going to work. Let's plug in that 30. Let's try it. So if we plug in 30 into this equation, we get how much? $8.50. All right, so if I spend $8.50 of that 15, how much money do I have left? $6.50. So she would have $6.50 to spend on lunch. Bro, she could go to Chick-fil-A and get like a sandwich. Maybe. I don't know. Their prices have gone up, right? Like a kid's meal, yeah. Like she can get a 3-nugget meal. I don't know. Be rough, homie. So one thing I want you to note on here is that this second one, this 150 to 170, we saw this written like this. It's the same thing. Okay. Down here on this one, this is written as 0 to 50. Okay, so again, I want you to answer these questions. You're putting true or false. You got to put why you think. Okay, don't say just because I think so. No. Okay. This you're going to try to turn in before you leave, but if you don't get it done, you're going to finish it up for homework. Okay. Again, my homework is if you don't get it done in class, you got it home. You got to take it home. Okay. I don't want you to have homework. So take the next couple of minutes and work on that. No, you just have to do this side. Look at the top and make sure it's the one that looks like that.